Analyzing changes in sun's altitude, shadow problems. Hello everyone. Today we are going to begin a new subsection titled Analyzing Changes in the Sun's Altitude, specifically focusing on what we call shadow problems. In this lesson, we are going to explore the dynamic relationship between the position of the sun in the sky and the length of the shadow cast by an object. You might have noticed this in real life. As the sun moves across the sky throughout the day, its angle of elevation changes, and this change directly affects how long or short a shadow becomes. Over the next few slides, we will learn how to use trigonometry to model these changes and solve for unknown heights and lengths. Understanding the concept. First, let's visualize why a shadow exists in the first place. A shadow is simply formed because an object stands in the path of light, blocking the sun's rays from reaching the ground. The most important thing to understand here is that the length of this shadow isn't random. It depends entirely on the angle of elevation of the sun. Think of the angle of elevation as how high the sun sits in the sky. There is what we call an inverse relationship between this angle and the shadow's length. To put that simply, as one goes up, the other goes down. When the sun is low in the sky, meaning we have a small angle of elevation, the rays hit the object at a shallow angle, creating a very long shadow. Conversely, when the sun is high in the sky, meaning a large angle of elevation, the shadow becomes much shorter. As we move through the upcoming examples, keep in mind the constant factor. In almost all these mathematical problems, the height of the object, which we will represent as h, stays exactly the same. Only the shadow length and the angle change. Finally, I want to give you a hint on which mathematical tool to use. Since we are dealing with the height of the object, which is the side opposite to our angle, and the shadow length, which is the side adjacent to our angle, the tangent ratio, or tan, is going to be our most effective tool for all our calculations. Keep this in mind, because in the next slide, I will show you exactly how to turn this concept into a step-by-step mathematical model. Now that we've introduced the topic, let's dive deeper into the core concept behind these shadow problems. Step-by-step mathematical modeling. Now that we understand the relationship between the sun's angle and the shadow's length, let's move on to the most important part, the strategy. To solve these problems where the shadow length changes as the sun moves, you shouldn't just jump into calculations. Instead, I want you to follow this systematic, 5-step mathematical modeling process. Step 1 is all about defining your variables. Before you touch any numbers, assign letters to what you don't know. Let's let h represent the height of the object. Let's use x to represent the initial length of the shadow. And finally, let's use d to represent the change in shadow length. This is the specific distance by which the shadow either increases or decreases. Step 2 is where we set up our first scenario. Look at the problem and identify the first angle of elevation, which we will call θ1. Using the tangent ratio we discussed in the previous slide, you will relate the height to the initial shadow length. This gives us the equation, tangent of θ1 equals h over x. Step 3 is setting up the second scenario. Now, identify the second angle of elevation, which we'll call θ2. This is the crucial part. If the shadow has increased by our distance d, your new shadow length is no longer just x, it is now x plus d, so your second equation will be tangent of θ2 equals h over x plus d. Step 4 is creating a system of equations. At this point, you have two separate equations, but you still have two unknowns, h and x. To make this manageable, your goal is to rearrange both equations so that you are expressing h in terms of x. Finally, step 5 is to solve via substitution. Since both equations are now equal to h, you can simply equate the two expressions. This will leave you with an equation containing only x, which you can solve. Once you have found the value of x, you can plug it back into either of your original equations to find the height, h. Keep this roadmap in mind, because in the next slide, we are going to apply this exact step-by-step method to a real-world example. Real-world example. Take a look at this scenario. Imagine a vertical pole standing on the ground, casting a shadow. we are observing this at two different times. At the first instance, the angle of elevation of the sun is 60 degrees. As the day progresses, the sun moves lower in the sky, and the angle of elevation decreases to 30 degrees. We are also told that because the sun is lower, the shadow has lengthened, specifically increasing by 20 meters. Our goal is to determine the actual height of this pole. To solve this, we need to start our step-by-step solution by identifying our constants and our variables, just as we discussed in the previous slide. First, let's define the height of the pole as h. This is our constant value that remains unchanged throughout the problem. Next, let's represent the initial length of the shadow, the one formed when the sun is at 60 degrees, as x. Finally, we must account for the change in length. Since the shadow increases by 20 meters when the angle drops to 30 degrees, the new, longer shadow length will be represented as x plus 20. Now that we have understood the theoretical framework and the step-by-step modeling process, let's put everything into practice with a real-world example. By setting up our variables this way, we are now perfectly prepared to move into the next slide, where we will formulate our trigonometric equations. Formulate equations for real-world example. First, let's formulate the equation for the first position, where the sun is higher in the sky at 60 degrees. If you look at the right-angled triangle formed by the pole and its shadow, we apply the tangent ratio we discussed earlier. We have tangent of 60 degrees equals height h over the initial shadow length x now. Remembering our trigonometric values, since tangent of 60 degrees is equal to the square root of 3, we can rearrange this to isolate h. This gives us our first important equation. H equals x times the square root of 3. Let's label this as equation 1. Next, we need to formulate the equation for the second position, when the sun has moved lower in the sky to 30 degrees. As we noted in the previous step, the shadow has now increased by 20 meters, so the total length of the shadow is now x plus 20. Looking at this second right-angled triangle, we have tangent of 30 degrees equals height h over the new shadow length, which is x plus 20. Since tangent of 30 degrees is equal to 1 over the square root of 3, we can rearrange this to solve for h as well. This gives us h equals the quantity x plus 20, all divided by the square root of 3. We will call this equation 2. Now that we have identified our variables and set up our initial scenario in the previous slide, let's move on to the actual formulation of our equations. This is where we translate our geometric picture into algebra. Now we have two different expressions that both equal h, which sets us up perfectly for the next slide, where we will equate them to solve for x. Solve for variables in real-world example. First, we will equate the two expressions for h dollar. Since both equation 1 and equation 2 are equal to h dollar, they must be equal to each other. This gives us our working equation. X times the square root of 3 equals the quantity x plus 20, all divided by the square root of 3. Next, our goal is to solve for x dollar, which represents our initial shadow length. To get rid of that fraction, we will multiply both sides of the equation by the square root of 3. When we multiply the left side, x times the square root of 3, by the square root of 3, we are left with just 3x dollar, because the square root of 3 times itself is simply 3. On the right side, the square root of 3 in the denominator cancels out, leaving us with just x dollar plus 20. Now we can simplify this to find x. We have 3x dollar equals x dollar plus 20. To isolate our variable, we subtract x dollar from both sides, which leaves us with 2x dollar equals 20. Dividing both sides by 2, we find that x dollar equals 10 meters. Now that we have established our two separate equations for the height, h dollar, from the previous slide, we are ready to bring them together to solve the problem. Now that we have found the value of our initial shadow length, we can move on to the final step, calculating the actual height of the pole. Calculate the height in real-world example. Now that we have successfully found the value of x, which is 10 meters, we have reached the final step of our calculation, finding the actual height of the pole. To do this, we simply take our value for x and substitute it back into our first equation. Remember, equation 1 was h equals x times the square root of 3. So, by replacing x with 10, we get our height, h equals 10 times the square root of 3 meters. Now, if you need a decimal answer for a practical application, we can use the approximation for the square root of 3, which is roughly 1.732. When you multiply 10 by 1.732, we find that the height of the pole is approximately 17.32 meters. And there you have it. We've moved from the initial shadow measurements all the way to determining the height of the object itself. Let's take a moment to review the key takeaways from this entire process. Key takeaways. Now that we have successfully worked through that example and found the height of the pole, let's take a moment to recap the key takeaways from this lesson so you can apply them to any similar problem you might encounter. First, always remember that the height of the object is constant. Whether the sun is high or low, the pole or the building itself isn't growing or shrinking. It is only the shadow length and the angle of elevation that are changing. Second, when it comes to your trigonometric tools, the tangent ratio is your best friend here. For these specific shadow problems, you should always use tangent theta equals height divided by shadow length. This is because we are almost always dealing with the vertical height as the opposite side and the shadow on the ground as the adjacent side. Third, keep a close eye on the logic of the shadow length. There is an inverse relationship here. A smaller angle of elevation, meaning the sun is lower in the sky, will always result in a longer shadow. Conversely, a larger angle means a shorter shadow. Finally, regarding your algebraic strategy, the most efficient way to tackle these multi-step problems is to express the height, h, in terms of the shadow length for both given angles, and then set those two expressions equal to each other. By equating them, you can isolate and solve for your unknown variable. Before we wrap up, I want to briefly touch upon some common pitfalls to avoid, so you don't lose marks on simple errors in your next exam. Common mistakes to avoid. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even if you understand the concept of the sun's altitude, it is very easy to make a small error that leads to the wrong answer. Let's look at 4 specific mistakes to watch out for. First, watch out for incorrect ratio selection. I have seen many students mistakenly reach for sine or cosine. However, if you look back at our modeling steps in slide 3, you'll remember that we are dealing with the height of the object as the opposite side and the shadow on the ground as the adjacent side. Because we are working with opposite and adjacent, tangent is always your correct choice. Second, be very careful not to misidentify the shadow length. This is a big one. You must distinguish between the initial shadow length, which we called x, and the change in length, which we called d when you are setting up your second equation, like we did in our example with the pole. Remember that the new length is the total length, which is x plus d, not just the increased d by itself. Third, keep an eye on your calculations involving the square root of 3. In our example, we had to multiply the square root of 3 by itself to solve the equation. It is easy to get lost in the algebra, so always remember that the square root of 3 multiplied by the square root of 3 equals 3. Finally, do not confuse your angles. Always use your logic to check your work. A larger angle of elevation, like 60 degrees, must be paired with the shorter shadow, while a smaller angle, like 30 degrees, must be paired with the longer shadow. If your math shows the shadow getting shorter as the sun sets, you know something has gone wrong. Keep these tips in mind, and you will be able to tackle any shadow problem with confidence.